meaning acceleration is 0. Okay? So that's the first law. Now it turns out that Mr. Galileo was the one who discovered this law. But the reason we call it Newton's first law is because it's really a special case of the second law, which Newton discovered. What Mr. Newton discovered was the acceleration of an object was proportional to the force acting on it. You double the force acting on an object, the acceleration doubles. And so the first law is just a special case of this. When force is 0, acceleration is 0. Okay? So the first law is a special case of the second law. So Newton's second law is the force acting on an object. When a force acts on an object, it gives the object an acceleration. The proportionality constant is its mass. Greater the mass, smaller the acceleration. Yeah. So for instance, you can apply a force to a truck and its acceleration will be small. Apply the same force to a car and the acceleration will be greater. Yeah. So the units are, the units, SI units for mass are kilograms, acceleration is meters per second square, and this combination kilograms, meters per second square, we call it a Newton in honor of Mr. Newton. So the units of force are newtons. Yeah. In the US British units, mass has units of slug, acceleration is feet per second square, and slug feet per second square is a pound. Okay? But we don't use that too much. We will use the SI unit. So here's an interesting fact. So this is a vector equation. Okay, so this vector is equal to that vector. When two vectors are equal to each other, what that means is their components are equal to each other. Okay, so the x component of the force is equal to m times x component of the acceleration. Y component of the force is that, and so on. Now here's an interesting fact. So if you apply a force in the y direction, you only give acceleration in the y direction. Okay? So if this is 0 and this is 0, then those accelerations will be 0. Okay, so you apply a force in the y direction, you can only change the motion in that direction. You apply a force in the x direction, you can only change the motion in that direction. Okay. So, okay, applying a force in the y direction, you can't give an acceleration in the x direction. Okay. All right, so the motion along 3 axes are independent of each other. So the acceleration along an axis is caused by the net force component along that axis only. Okay. So if you want to cause an acceleration in the x direction, only the force in the x direction causes that. Motion along the 3 mutually perpendicular directions can be treated independently of each other. Now Newton's third law implies all forces come in pairs. So for instance, this lady is pushing off on the wall, and the wall applies an equal and opposite force on the lady. That's what propels her. Okay, so action and reaction are equal and opposite. So that's how you'll hear this law. Okay. So you see, forces come in pairs always. Okay. And you see this all the time when you want to walk. So let's say I want to propel myself forward. How do I walk? I'm pushing backward on the floor. And the reaction force of the floor is propelling me forward. So for instance, if I was an icy surface, my foot would slip. I couldn't apply a force backwards on the floor. And I would move forward. Okay, so the faster I want to propel myself, the greater the force I have to apply. Right? Then it'll apply a greater force forward. You guys have you guys seen what is that quarter-mile race? I'm sorry? The cars that go a quarter mile. Drag racing. So you guys, it's a race, so you want to get there as fast as possible. And you guys see they burn their tires before they start. So why are they burning their tires? Get more grip on the ground, so you can push with a greater force and you get propelled with the Yep. So that's Newton's third law. Action and reaction are equal and opposite. Yep. So in that equation, mass tells you how much stuff there is. Okay, greater your mass, smaller your acceleration for a given force. Okay. So this is also called inertia. Okay. The greater inertia you have, the harder it is to accelerate you. Okay. So mass is a measure of the object's resistance to change in its motion. Greater the mass of an object, smaller its acceleration under a given force. Mass is a scalar, so you see that's a scalar multiplying a vector, and that's a vector equal to that vector. I put this picture here because the mass of an astronaut is the same. His weight is different on different objects. His weight on the moon is 1/6 his weight on the Earth. That's because the acceleration due to gravity on the moon is 1/6. Okay, but his mass is the same. Okay, when several forces act on an object, the effect on the object is the same as this one single net force. So what we're saying is, if these two forces act on an object and this one single force, which is the sum of the two forces act on an object, from the motion you can't tell if it's two forces acting on the object or one force acting on the object. Okay? So the effect of these forces is the same as the effect of this force, the sum of two forces. So the superposition principle says when several forces act on a body, the effect is the same as that of a single resultant force. A single resultant force would give you the same motion as these forces. By the way, so here's the definition of Newton. You're applying a force of 1 Newton. When applied on a 1 kg mass, you give it an acceleration of 1 meter per second squared. If you apply 1 Newton on 1 kg, you give it an acceleration of 1 meter per second squared. So here's the Earth. When you're standing there, Earth exerts a force of gravity on you. And the force of gravity, which way does it point? It points towards the center of the Earth. Yeah. So that's the reason why you don't fall down when you're in Australia. Yeah. So the force is toward the center of the Earth. The magnitude of this force is called your weight. Yeah. So the direction of that force is toward the center of the earth, and the magnitude of the force is, okay, so the magnitude of the gravitational force is called your weight. So the force is always directed toward the center of the earth, and the magnitude of that force is your weight. By the way, you feel your weight, right? So what is it that you're feeling? Are you feeling the earth pulling down on you? What's that? I'm sorry?
You're feeling the ground pressing back.
That's right. Okay? So the earth is pulling down on you, but you don't feel that. What you're feeling is the ground pushing up on you. So what our friend is saying is, for instance, let's say we pick up this room, go up a mile and drop the room. Okay? And then you'll feel weightless. Because when the room and you are falling together, nothing is pushing you. Okay? So when you say you're feeling your weight, it's really you're feeling the force that the ground exerts on you. Okay? So for instance, if you want to feel weightless, you can do the following. So when you stand on a scale, earth is pulling you down, and it's this push that you feel. Now if you do the same thing underwater, there's a buoyant force on you. That is, the water is pushing you up, and we'll talk about this in chapter 14. Then this force is almost zero. So if you weigh yourself underwater, the scale will read 0 pounds. All right, so the gravitational force is the force with which Earth attracts you. This is the gravitational force. And the magnitude of this force is your weight. The normal forces, so again, Earth is pulling down on this laptop. There's the Earth, okay? And what happens is, so there's the laptop. And see, the atoms on the laptop and on the table push each other, and these atoms are pushing on the laptop. Okay, and that's called the normal force. And this force is equal to that. Yep. It's called a normal force because it's always perpendicular to this interface. It's always perpendicular to this surface. And perpendicular is also called normal. Okay, so this is the normal force. Okay, so right now there's a normal force acting on this object, and it's equal to the weight of the object. But if I press down on the object, now the normal force increased. Okay. All right, so this will be the last thing we'll do today. We'll be dealing with objects on an inclined plane. So let's make sure we understand this diagram. Okay. So what we'll do is we'll represent this object by a point. The inclined is defined by this angle. So that's the angle of the incline. The Earth pulls down on this fellow like that, mg. But what is useful is not this force, but what we want is the component of the weight along the incline and the component perpendicular to the incline. Those are the two things that are useful. All right, so this is theta. This angle is 90 minus theta. And so this angle is theta. Everybody understand that? All right. So this component of the weight is mg sine theta. So there's the hypotenuse. This component is mg sine theta, which is equal to that. And this component is mg cosine theta. Okay, so that's what's shown here. There is the weight of the person. The component perpendicular to the incline is mg cosine theta. The component parallel to the incline is mg sine theta. Okay, so just memorize that. So if you're on an incline, of angle theta, the force parallel to the incline is mg sine theta, and the force perpendicular to the incline is mg cosine theta. Okay. And that's the resolution of this, of your weight, that's most useful. So okay. The component parallel to the incline is mg sine theta. Okay, so now imagine a rubber band. So you're holding a rubber band and you stretch it. So if the rubber band is under a tension of 10 pounds, what does that mean? What is the rubber band doing to your right hand? It's pulling you with a force of 10 pounds. What is the rubber band doing to your left hand? I'm sorry? It's pulling you with a force of 10 pounds. So when you say that the rubber band is under the tension of 10 pounds, whatever it's attached, it's pulling that with a force of 10 pounds. And in what direction is it pulling? I'm sorry? What the rubber band is trying to do is it's trying to get smaller. It's trying to get shorter. Okay? So for instance, if this was a rubber band and it was under a tension of 25 pounds, this rubber band is pulling this object with a force of 25 pounds. And this rubber band is pulling this object with a force of 25 pounds. Okay? So, of course, I just use rubber bands to illustrate. Ropes are under tension. Wires will be under tension. So when you say that a wire is under tension of 100 pounds, that means it's pulling whatever is attached to the wire with a force of 10 pounds, 100 pounds. And in what direction is it pulling? So what is the wire trying to do? It's trying to get smaller. Okay? So that's tension. All right, we'll stop here. This is a sort of a longer story, so we'll